And this is what we saw last class. We said that for a given location, when we're drilling a wellbore, we can set two bounds for managing the mud density in the wellbore. And those were, we call it a lower bound and an upper bound. That's basically how low you can go on mud density and how high you can go on mud density. Notice, this is very important. This is not a plot of pressure as a function of depth. This is a plot of gradient as a function of depth. Okay? It's not the same. And usually these lower bounds and upper bounds, the gradient increases as depth increases. But remember, this is not pressure, okay? Here, hydrostatic pressure looks as a vertical line, like this one. So if at a given location, like for example, in this section, you're drilling this section and you have a constant density of the mud inside the wellbore, this is going to be the gradient, and the pressure is going to be hydrostatic. It's going to increase linearly with depth in this location. But the gradient everywhere is going to be the same. Okay, so what I'd like to discuss now is how we set these lower bound and upper bounds based on what we already learned and a few more things. And basically that's going to give us what is called the mud window and the range, operational range at which you're going to set up your casing depths. All right, so how do we do that? Well, I added here some values that were obtained from the previous example. Let's imagine that we're drilling somewhere over here at this depth, and that was the 7,000 psi that we were working with before, and we want to determine what is the lower bound and what is the upper bound based on what we know. Okay, so at that particular depth, at 7,000 feet, in the previous problem, we calculated pressures in the wellbore for shear failure, for a breakout of 70 degrees, and for obtaining tensile fractures, right? Before I write those, let's write two other very important quantities. First of all, the pore pressure. What was the pore pressure in the previous problem at 7,000 feet? I have it over here. It was 3,080 psi, right? So that would be, let me zoom in a little bit more. That would be somewhere over here. And that results in a gradient, equivalent gradient of 8.3 pounds per gallon, right? So that's something that you cannot change. Whatever you do when you're drilling, that's an initial condition. And that's something that you're not going to change by changing the weight of the mud, for example. Question: do you want to drill above or below the pore pressure in the formation? Above, right? Most of the times you want to drill above because otherwise your drilling fluid is going to get into the formation. That's what we call overbalanced drilling. Underbalanced drilling will be when the pressure in the wellbore is below the pore pressure, and sometimes you may want to do that, and you may be able to do that, especially in shales. And sometimes you want to do that in sensitive shales so that the fresh water from the mud doesn't get into the shale. And if it doesn't get into the shale, it's not going to swell it, and it's not going to cause some chemical issues that we're going to discuss later on. But usually we want the pressure in the well to be above this number. Okay, this one sometimes is going to work as an absolute lower bound. That means that you may not want to go below that one, most times. For an absolute upper bound, we have the minimum principal stress, which in this case it's a horizontal stress, and it's equal to, let's say, 1, 2, 3, somewhere over there, to the minimum principal stress, and in this particular problem was 4,300 psi. You may not want to go above this number either. Why not? If you go above this number, it's very likely that you may propagate a hydraulic fracture, and not just a tiny fracture, but a long fracture. If you overcome the minimum principal stress, the rock may split apart and you will create a very large hydraulic fracture. So this one is going to work also as an absolute upper bound. You may not want to go above this number. We'll discuss a little bit more about this, but let's just keep in mind these two important numbers, okay? So now we know that more or less our window should be somewhere over here, okay? But we're going to constrain that a little bit more. And for that, we're going to use what we computed last class. And first of all, we computed the breakdown pressure. And the breakdown pressure was 4,320 psi. So just a little bit larger than S3. This was PV, and the equivalent mass density was 11.6 ppg, and according to this value we could go a little bit further in extending the mud window to 20 psi more. Let's see, then we also had the pressure in the wellbore for a breakout of 70 degrees, and that was equal to 3660 and 9.8 pounds per gallon. So PWBO 70 degrees, it was right here, and it was equal to 9.8 ppg. Okay, so now we have a little bit more of data here in order to constrain the stability of the wellbore. Before we say, okay, we don't want to go below the pore pressure, but if you were to drill with this weight, you will get breakouts which are larger than 70 degrees, and they may cause wellbore collapse by shear around the wellbore. So you need more support in order to have that wellbore stable. So your lower bound, according to these two, which one will you choose? The pore pressure or the one for the breakout? The one for the breakout, right? It puts there a tighter constraint into the lower bound. So I'm going to choose this one as the lower bound, because otherwise I'm going to have a lot of shear failure on the wellbore. What about the upper bound? What would you choose? PV, which let me write here in terms of absolute value, is 4320 psi, or minimum principal stress. I know in this case they are quite close, right? But let's imagine they are a little bit further away, 100 psi or something like that. What would you choose? I hear minimum principal stress. Why?
Because it's the limit where if you actually exceed it, then you're going to have a fracture.
Yeah, but according to the Kirsch equations, you can go a little bit higher.
But how high?
According to this example, 20 psi higher.
And you wouldn't get like a fracture. And what do you mean we can't go high enough? It's not going to crack.
It's going to crack. The wellbore is going to crack. If you go, say, if you go 4310, and if this is correct, no. Let's make an example. You go to 4321, it's going to fracture, right? And It depends now. It depends on which one is larger. And let me explain this a little bit more in detail, because the solution is not going to be the same all the time. All right. So, but we're going to find a solution here to this problem. But before we say something about that, let me say what's going to happen in this case. Let's imagine that we have a case like this one in which PV is higher than the minimum principal stress. If that's the case, and if this is true, and I drill with the pressure in the wellbore larger than PV, what is going to happen is that if this is a wellbore, when you get to a pressure larger than PV, you're going to create a tensile fracture because you went over PV. But not only that, if your pressure is larger than PV and PV is already larger than S3, very likely this fracture is just going to propagate and create a large hydraulic fracture. Why? Because the pressure inside the fracture is already larger than the minimum principal stress. Of course, there are a few more things like viscous losses, opening actually the fracture, a few more details that we're going to see later on when we talk about hydraulic fracture propagation that require that pressure to be actually a little bit higher than S3. But just to play on the safe side, let's assume that here, if you have a pressure in the wellbore and in the fracture in this case higher than the minimum principal stress, this is going just to lead to a hydraulic fracture that propagates out of the wellbore, and it goes very far. But this is not going to be the case, however, on some cases where actually S3 is higher than PV. And why you will have these two scenarios? Because sometimes the stress and isotropy may be different. The tensile strain of the rock may be different, and so these values can switch. What happens in this case? If we drill with a PW larger than PV, but this one is still smaller than the minimum principal stress, the result is going to be that you are over the value of PV, so you're going to have a tensile fracture, but just very close to the wellbore, because that pressure is smaller than minimum principal stress. It's not going to propagate far away from the wellbore. Far away from the wellbore, you have more stress that impair the propagation of that hydraulic fracture. But close to the wellbore, because you modify the stresses around the wellbore, these are what are called near wellbore effects. You happen to have a stress which is more tensile in this direction and which produces a tensile fracture in the rock, but the fracture will not propagate. And that will lead to small tensile fracture. In fact, sometimes this may not be bad, and you can have tensile fractures and your wellbore can be stable. For example, that is the case of some of the wellbore images that we saw a couple of lectures ago, in which we have images of breakouts, we have images of tensile fractures, And if you can image that, it's because that wellbore is stable. It's not failing. Let me see if I get to that quickly. Let me ask you about the homework. Do you guys follow the Python notes to solve the homework? No? Not many? Raise your hand if you actually do. No? No one? So the notes are put in terms of a Jupyter notebook, and Jupyter has built-in Python in it. So that's why, or that's how I wanted to put some quota of coding in it by showing you the solution with a Python code. But you don't look at that. No? Okay, well, let me check that, and I'll get back to you. But remember, that's another resource that you can use. All right, so let's see. Tensile fractures, shear fractures. This is the image I was meaning, right? So here you can see we have breakouts, we have tensile fractures, but that way we're stable. So it's going to be very important when you actually have to take a decision. In this case, what is going to be your upper bound? Because if PB is larger than S3, sometimes, just to be safe, you may want to set the upper bound to the maximum principal stress, not to PB. Okay? And for example, in this case, if I'm safe, I want to play on the safe side, I will say that my maximum upper bound is going to be S3 and not PB, because PB is larger than S3 in this particular example. And these are the two values of lower bound and upper bound that I put in here in order to define the mud window as a function of depth. So let me clarify that this is just going on the safe side, okay? But you could choose otherwise. You could choose PB. And if you know that location, that actually the tensile strength is very good and the rock is more or less homogeneous, so that you don't have variations that will lead you to low circulation at some depths, you could use PV. Furthermore, in some locations, if your Kirch equation is not working very well, you may just go ahead and determine some of these upper bound directly, not with equations of Kirch, but you run a leak-off test. With the leak-off test is going to tell you exactly what's the maximum value of the upper bound. And this is where the art of the drilling geomechanics comes into the picture, is to enlarge this window, to move this lower bound to the left and the upper bound to the right, so that you have the maximum window possible. I don't know if you guys took a class with Professor Gray, but Professor Gray is a world-class driller, and he ran for many years a research project that was called wider windows. And the objective of that is to make that window of drilling more flexible, so you reduce the number of casings, and you reduce also non-productive time and all those things. But how do you do that? Well, by setting these bounds. And how do you set those bounds? By knowing what is happening in the wellbore. If you have shear failure, what is the shear strength of your rock? Or if you have here a tensile fracture, how far you can go in that tensile fracture? And even sometimes you can add some materials in the drilling mat that help you move this window a little bit more. Those are called wellbore strengthening materials. Usually it's small particles that they plug small fractures so that you can go a little bit further on extending that window. But that depends on the properties of the rock and on the stresses in a particular site. But that's it. As long as you know that, this is everything I want you to remember from this part of the geomechanics for drilling. Sometimes it could get a little bit more complex. You may have some other operational issues for drilling. I'm not going to go through those. You'll see those in drilling. What I want you to remember from this part of the drilling of geomechanics is why you cannot have a very light mud, and that's because the rock is going to feel in shear. Why you cannot have a very heavy mud, because the rock is going to feel in tension and you're going to have a hydraulic fracture. How you calculate that, and also if you have failure, where those breakouts and tensile fractures appear around the wellbore and why. Okay, the homework is from problems 1 to 4, if I remember well. It's all about this, but just changing some parameters, like the properties of the rock, the depth, the pore pressure, and you will see how these two move. And sometimes you may be in some locations in which your lower bound set by shear is at the right of your upper bound. Well, that would be a location in which, in theory, you cannot drill a wellbore. You have a question? Yes.
Yeah, is it always true to choose, or safe to choose the minimum principal stress as your upper bound?
Yes, but sometimes you may be playing too much on the safe side. And although you'll be safe at that particular number, probably there is another guy that says, no, you can go higher. And if you go higher, I'm sure that doing my calculations, or I have drilled a wellbore before, we can save one casing. So this is a safe option. But sometimes you could go either with the value of PV or with the actual value of PV that comes from the leak-off test and go a little bit beyond that. So that's when the expertise comes into the picture in order to see which one you actually choose. But the safe one will be the minimum principal stress. Okay, so are you guys ready to talk about deviated wellbores? Okay, so far we discussed vertical wellbores, and deviated wellbores are not a lot different, but you need now to put all the concepts of a vertical wellbore into a deviated wellbore. So let's get started with that. Let's say that we have drilling path, and we're going to drill a wellbore, and in this location the north is towards the back of the page, east is this direction, and down is in this direction. And I know for this particular place that somewhere in the subsurface the conditions of stress are like this. We're going to do an example of normal faulting because that's what we see in most of the unconventional formations in the US. Let me make this a little bit larger. And we're saying that SB is larger than SH max. larger than SH mean. And in order to get a horizontal wellbore, many times we do start with a vertical wellbore. Okay? All right. So I got to this depth, close to the pay zone. I like to do multi-stage hydraulic fracturing. In which direction should the well go? Towards the east, towards the north, northeast? Why east? Because it's parallel to the minimum principal stress, right? Remember, this one here is S3. So, yes, a wellbore that is meant to maximize hydraulic fracturing will go into that direction. Okay, so let's just imagine that we also drill another wellbore from the same drilling pad, and it has step out somewhere around there, but this one goes in direction north-south. Okay. What I like that we do is that we analyze the stresses around the wellbore for these two deviated wellbores, for the laterals, but also for the vertical. Let's start with the vertical, which is something that we already know. Let's say this one, location 1. Which plane in here is perpendicular to the wellbore at location 1? The plane of SV, the plane of SH min, or the plane of SH max? The plane perpendicular, let me be more precise, the plane perpendicular to SB, right? So if I were to analyze a vertical wellbore in this location, what I would do is I'm going to draw this in 3D, okay? Or I'm going to try to do that. And well, let me be a little bit more organized here. I'm going to draw everything from left to right. I just have to move a little bit over here. So I'm just drawing the top face of that cube over here. This is going to be the wellbore, the cross section of the wellbore in that plane. And according to these conditions, I have SH min coming east-west and SH max coming in direction north-south. My question here is, where are you going to see the breakouts? Tell me, remember that now we are tying this to a geographical coordinate system. So the breakouts in the vertical wellbore are going to appear on the north and the south, on the east and the west. East and west. Everyone sees why that, east and west. So this one is the largest, SH max is the largest between SH max and SH min. Therefore, if you were to see breakouts, they would occur where compression stresses magnify the most. And if you got tensile fractures, they would happen in direction north-south. Okay? So we already knew that's apart from the vertical wellbores, right? And this is plane number 1. Okay. What about now? Let's do this location. Number 2, a wellbore going in direction south, from the north towards the south, a lateral wellbore. Which plane of the cube should I use for that case? The one perpendicular to SH max, right? Everyone sees why. So this is the wellbore direction, right? So I want a face of the cube which is perpendicular to that direction, and that's the plane perpendicular to SH max. So if I put that face of the cube over here, and I have a cross section of the wellbore, the stresses acting on that plane are going to be SV and SH mean. Right? So let me move. So you see SV is going down in this direction and SH mean is going from the side. So this is what I have at that location. Okay, again, where would you expect the breakouts to happen? And now there is another option for this. You can tell me top and bottom, or the sides, or somewhere else around the wellbore. Breakouts, yeah. Where would the breakouts form? Yeah. Okay. I think you could say also east-west, but that would mean on the sides, right? On the sides, or on the top and bottom. Anyone says top and bottom? No? It's gonna be on the sides, right? Here. Why? Because SV is larger than SH mean in this particular normal faulting case, okay? Remember that, this is for normal faulting. If we were in another location with reverse faulting or strike slip, it's not going to be the same. But in this case, SV is larger than SH mean, so all the compression magnifies in here. And if you had tensile fractures, they will occur on the top and bottom of the wellbore. All right, so let's do number 3. Number 3 will be the wellbore that we were saying that will be the optimal one for hydraulic fracturing. And let's say it's somewhere over here. And for that, we need to use the plane perpendicular to SH mean, and that plane is this plane. The cross section of the wellbore will be that one, and here I have SV and SH max, and I have SV in this direction. Okay, breakouts, where would they happen in this case? Top and bottom, or on the sides? On the sides again, okay? And if there are any tensile fractures, they will be on the top and bottom. Okay, so let me ask you, in which case you think it's going to be more likely to have breakouts? For a wellbore in the direction of SH max, which is this one, or a wellbore in the direction of SH mean? It's a tricky question.
I think it's the opposite. Like, whenever the difference is not a lot, you're gonna have more breakouts, right?
Yeah, I think you're going to the right direction. Actually, we cannot answer that because we don't know what is SH max. We just say that it is larger than SH mean, but smaller than SV. But actually, it would depend how far SH max is from SV and SH mean. That's the differential stress that goes into the equations. The more differential stress you have in the plane perpendicular to the wellbore, the more likely you're going to have breakouts or tensile fractures. Or say it a little bit differently, the more differential stress you have, the narrower also is going to be the mud window. Because differential stress, the load that you put in addition to the background stress is what is really causing here shear failure and tensile fractures. And that's what you have to do in the laboratory, and I think some of you already did this morning, adding a differential stress to produce breakouts and tensile fractures. Yes?
Isn't your SH max always going to be higher than your SH mean anyway?
It is, but here we just want to see what is the difference between SV and SH mean and the difference between SV and SH max. Now you don't know that information. Okay, one more thing, and this will be for the wellbore stability part. This is what I want you to recognize, where breakouts and tensile fractures would occur in a horizontal wellbore, and what are the stresses involved in it, and what are the stresses that you need to put into the Kirsch equation. So far in the Kirsch equation that we have used, we also always used SH max and SH mean. Well, now, if you have a deviated wellbore, you have to replace SH max by the largest stress at that particular location, and SH mean by the least stress at that location. So the Kirsch equations are going to be exactly the same. It's just that you have to change the values of the stresses. Perpendicular to the wellbore in that plane, you need to see which is the largest, which is the minimum, and use those two in the equations for Kirsch. We'll talk a little bit more about that on Friday. But let's try to continue thinking about this and extend this to hydraulic fracturing. What would be the direction of a hydraulic fracture in this particular place? What would be the plane that you would expect in here? A vertical wellbore, a vertical plane with strike, what strike? 0, 0, 0, or going in direction north-south, right? Okay, so that means that if you were at a location like this and your value of pressure in the wellbore goes above PV, and you may extend the fracture that is going to be a plane. I'm trying to extend these fractures out of the plane. It will be a plane like that one, right? In 3 dimensions. It's perpendicular to the minimum principal stress, SH mean, and that seems correct. So if this one will try to enlarge here in this location, it's just going to grow like a plane perpendicular to SH mean, something like that, right? Let's see for that case. Case number 2, if those fractures continue growing, they will form a plane which is also perpendicular to SH mean, and where those planes are perpendicular to the minimum principal stress. And if they will continue growing and create a large hydraulic fracture, it's just going to grow like this and perpendicular to SH mean. Well, let's see what happens in the third case. In the third case, when you are forming these fractures near to the wellbore, this is what you would expect: a plane which is perpendicular to SH max. Can you see that now? That around the wellbore, the minimum principal stress is actually in that direction, and those are the fractures that you would expect. But that plane is not perpendicular to the minimum principal stress, right? So what do you think it would happen if that fracture continues growing out of the wellbore, outside of the influence of the wellbore and the near wellbore effects? 30 more seconds, okay? It would Now it's like this. As it gets outside of the wellbore, and if it can, it will twist and get into the shape, which is perpendicular to the minimum principal stress. So it will start as a plane like this, but then it will twist onto a large hydraulic fracture that will be perpendicular to SH mean further away from the wellbore. One more question: how do you avoid this? You don't want to have that because propane is not going to go through, and a lot more things that are not good. How do you avoid that? You do perforations. Okay. All right. Okay. See you guys on Friday, right? Okay.